Hello, hello, hello. Welcome back. It is Thursday, the 20th of November, and today I'm going to round out what I think is the last of the important interview skills for Oxbridge interview, which is the one that I think the most people want help with, which is the really out there questions. What do you do with the question that just knocks you for six right out the bat, where you look at it and think, what? How? What and why? And so today I'm going to present a few of those of different styles and hopefully give you some of the skills that will allow you to tackle that, or at least put in a good enough effort that you can walk out thinking, yeah, you know what? All right, I kind of did that. I would say there are kind of two styles of this. One is where you are asked to do sort of equation work, where it is more syllabus based, but just the question is bizarre. So I've already presented one of these when I talked about my own interview, which for me was the metal spheres question, where I kind of looked at that and went, because there was a solution path which could be done, but it was just really hard to spot. And the other type is more discussion based. Where there's not necessarily a correct answer you have to arrive at, but they want to test that you can grapple with the different ideas that might be relevant. So some of these, if you see other videos online about interviews, some of them such as, I think I've discussed this before, what happens with a jet engine in the rain? These very open-ended questions, which are more designed to test that you can think on your feet about what things could be relevant. And it's almost like asking 1,000 different questions in one. So your brain goes firing off, and they can see how your brain would react if they had asked a different but similar question. So from your response to that, they can see what you would do in a number of different situations. So I've got a couple of questions in place now. If people join and people want to leave comments about specific questions that they've seen as well, I'm very happy to pivot and answer those if you want me to do a sort of sight unseen solve. Would be tricky with one of these out there questions, though, I will say, but I could at least demonstrate the process. So starting off, okay, let me get the whiteboard shared. So in terms of the out there questions, okay, let's start simple. So this is kind of easing in. This is less out there, but more sort of problem solving based, where it's not really to do with science. You're not really sure what it is, but hey, well, let's have some fun. So let's imagine, in fact, this is already lined up for us quite well. Let's imagine we have a square barn to the outside of which we are going to tether a goat. The side of the barn is 2A, and it is a square. And we're going to tether the goat with a rope of length 4A. And the question is, what is the range of possible grazing areas that the goat has access to? And so immediately you think by symmetry, all four corners are going to be the same. Kind of by common sense and logic, I would expect if I was like on the corner, that seems to be the best in terms of getting to a maximum grazing area. In fact, let me scroll down so that's more in the middle. So, okay, why don't I happen? Let's see what happens if I put the goat at the corner. So we know it has length 4A. So I'm just going to see where that has access to first of all. Got that dead wrong. So let me erase that. All right, so the goat is able to move 4A in any direction. So I expect it to go as a circle there. And then let's pretend that was a good circle. And then it would kind of be stopped by the walls of the barn there. Okay, but then it could turn and then pivot on that corner. So I might, and then I've got 2a left there, so I might expect it to make a circle like that. And same thing on this side, make a circle like that. So then in each of these, we have a quarter circle of radius 2a. A full circle of radius 2a would have area 4 pi a squared. So a quarter of that is just pi a squared in there. And this is 3/4 of a circle of radius 4a, pi times 4a squared, which is going to be 12 pi a squared. So the total is 14 pi a squared. And then let me consider what happens. Well, by logic, if all four corners are the same, and this is the maximum area, I expect the minimum area to be the furthest distance from the corners, which would be in the middle. Ooh, hello, Edward. Yes. You have a question based on A-level physics interview. Would I be able to help? Absolutely. Feel free to drop it in the comments and I'll have a go. So in the meantime, I'm going to consider what happens when we put the goat in the middle. So there's distance of 4a, 1, 2, 3, 4 in that direction, 1, 2, 3, 4. This is the distance, 1, 2, 3, 4. This is the unobstructed area that the goat has access to. And then I have distance 3a left here. So that's 3a, that's 3a. This is now pivoted on the corner and we'll have radius of 3a, which means it is a quarter circle that comes down to here. And same thing on this side. And from there then, I have a and a, so this becomes a quarter circle of size a. And you can kind of do that. So here we have 3a. Well, let's start with the big bit. Big bit is a half of pi times 4a squared. 16 pi a squared, 8 of that becomes 8 pi a squared. This is a quarter of pi times 3a squared. So it's 9 over 4 pi a squared, and the same over here by symmetry. And this would be a quarter pi a squared, and again, quarter pi a squared by symmetry. So then this becomes 10 over 4, which is 5 over 2 pi a squared. Double that up for this side, becomes 5a squared. So the total is 13 pi a squared. And that is the maximum area, and that is the minimum area. Now, is that sufficient? Does that satisfy? Could we consider, for instance, what happens as I move in between? Because I've kind of done that intuitively, and I'm wondering if I can kind of prove that scientifically. So that's when it gets a bit weirder. So let me apply some like qualitative understanding to this and say, the reason why the corner feels like it should be the biggest possible area is because you have the most unobstructed area that you're sort of seeing, for want of a better phrase. So for instance, if I'm attached in the middle, I only have 180 degrees of view as opposed to 270 degrees of unobstructed view. And here, I'm not going to be able to access something 4a away here because that would be going through the barn, which I can't do. I'm not sure. Well, at the very least, what we know for certain is as we move from a corner to the middle, we have access to 14. In fact, let me get rid of everything now just to clean this up a bit. No, overcleaned. Undo. Undo. Okay. Can we discuss why? Can I do better than that? Well, I know that if I touch it there, it's 14, then 13, then 14. I can't really think why the situation would be any different, although it might be fun to do a generic X, actually. where if that is x away from the corner, 1, 2, 3, 4 up there. 1, 2, 3, 4, and then in an extra one there. 1, 2, 3, 4, move out a little bit there. You'd have access to all of that, so you would still have a quarter of pi times 4a. So this 8, 4a squared, so 16, that's a half even. So this 8 pi squared is guaranteed wherever you do it. And then from here, this would be 3a plus x, which would come down here, which would leave you with x plus a, which would land you somewhere there. And this would be 3a minus x, which would land you somewhere like that. And then this would be 2a, and this would be a minus x, a minus x. So then we could get, sorry, I'm so into this now. Which, by the way, is exactly the kind of like getting stuck into the problem that they want to see, which is why I don't feel bad about showing myself doing all this. So you'd get that there. You'd get that there. You'd get a quarter of pi of a plus x squared there, and a quarter pi a minus x squared there. So you get that guaranteed, plus the sum of all of these. Go on. Let's have it. Pi over 4 into 9a squared and 6ax and x squared, plus pi over 4 into 9a squared minus 6ax plus x squared, where it's clear that these are going to cancel away through there, plus pi over 4 into a squared plus 2ax plus x squared, plus pi over 4 into a squared minus 2ax plus x squared, where again, these are going to cancel away when I add them all together. So you end up getting 8 pi a squared plus pi over 4 into 20 a squared plus 4x squared. And so this is the general area when I have it a distance of x away from a corner. I do feel like this should have been a minus somewhere, but No, because that implies, hold on, so that would be 8 pi a squared plus 5 pi a squared. Okay, I see. Plus pi x squared. So it becomes 13 pi a squared plus pi x squared. Oh no, but that's... (4x) Oh no, sorry, I laid out the problem entirely wrong. I defined it differently, but I think this would still work. So let me work this through. What did I actually solve for? That shouldn't have been 3a plus x. Because x was taken up. So let's say we place it at the corner. No, I just laid that out dead wrong. So what did I do? I probably did it x from here is how I laid that out from the actual numbers. Yeah. So I actually defined x as being x from the middle. And then that would be 3a plus x. That would be 3a minus x. So again, that ability to have a red flag, because I know what I expect the answers to be based on prior work. Did this predict something that no, this predicted when x equals 0, then I get 13 pi a squared, which is not correct if x was defined the way I defined it. So I was able to derive an expression, evaluate whether it predicted something physical, decide no, it doesn't, and so immediately sense that I should have backtracked. So that's how I caught that, and they like to see that. So it doesn't matter to them that I got it wrong in the first place. It matters to them that I was on it enough to track it, right? Also, Edward, I have seen your comment. I will come to it. I'm just so close to the end now. So here, x is defined as being from the end. And so clearly when x equals 0, we get the 13 pi a squared from what it is right in the middle. And for fun, now that we have a general expression, we can find the maximum area as we change x by differentiating and setting to 0, which is 2 pi x equals 0, which happens when x equals 0. In other words, maximum is 0. Sorry, minimum is 0, which we know from the middle, which implies there's only one turning point. But if we plot this area as a function of x, we see it is going to look something like this, where when x equals 0, it will pass through 13 pi a squared. And as we increase x, now obviously what I've drawn is slightly unphysical. X can't be negative for how we've defined it, so it kind of should start there. But we see the area only increases, but the maximum x can get is a. And when x is a, it becomes 14 pi a squared, which is our practically limited maximum. And so that proves it. That was a bit of fun. Right. Time for this comment. When I get given an unknown 6 marker, explain questions for A-level physics. Okay, let me read this comment. So when I get given an unknown 6 marker, those long explanation questions for A-level physics. So for example, using the kinetic theory of gases, explain why only small amounts of helium are found in the Earth's atmosphere. Even though there's lots of helium in the universe, and there was a lot of helium in Earth's atmosphere when it was formed, I just get a bit stuck. Even though I understand the kinetic theory of gases, I just can't seem to apply it to an unknown scenario like this. And I feel like this comes up a lot in the interview. That honestly is fair, because I find gas laws difficult as well. I remember when I was preparing someone for his Fiznatsky interview at Trinity. This was back when they used to do in fact, it was only like 2 or 3 years ago, but it's back when they used to do a written test right before the interview. And then based on your written responses, the stuff you got right, they would kind of leave, and the stuff you got wrong, they would lean into and really treat the interview like a mock supervision. One of those questions said something kind of similar to this, which was, if you spray a bottle of perfume in the middle of a spherical room, how long does it take the smell to hit the outside of the room? And I remember sitting with this student and just not getting it, because I remember I was like, somewhere in the back of my brain, I was like, okay, I know from my degree I could have done this at one point, and I've completely forgotten how. And the reason why is because you can use kinetic theory. Let me see if I can remember it. So we know that the average kinetic energy of a particle is 3/2 kT, which we also know, because it's the average kinetic energy of a particle, is a half m v squared for the root means. So for the mean square speed, which should actually be written like this. But the problem with that is that the mean square speed is just the square moving around, but it doesn't go straight to the outside. So Edward, I completely get what you mean about this being just sort of a little bit bananas, and like having to deal with like billions of particles moving around is a bit insane. What you can do in any situation, though, is first of all, remember you have a lifeline. The interviewer is an expert in their field. They know exactly what they're talking about. And even if you can't get there on your own, the point is for them to get you there with a bit of help. Because remember, an interview is a lesson, not a test. If you walk out having learned something, you know it's gone well. So what I would do in this situation is lay out what I do know. All right. And the way I would do that is just like haul the question back onto familiar territory by explaining exactly how it fits into the syllabus. So I would say, all right, here's what I know from the syllabus. I know that let's treat our I can use the time to state the ideal gas assumptions. The particles are very small compared to the container. There's a long time in between collisions compared to the time during a collision. We assume that the particles have no potential energy and do not interact except during a collision. We say that they have infinitely small volume. Um, we ignore rotational effects, all the usual things. And I can also lay out some equations that I know, like I did just here. Um, I can also obviously PV equals nRT. I remember pressure is proportional to density times temperature, but I can't remember exactly how that goes. If needs be, remember, this is not a knowledge-based test. They would kind of either get you to derive it on the spot, or they would present you an equation and get you to use it sight unseen, both of which are skills I've talked about before. In your particular case, let's think about your particular question, which is using the kinetic theory of gases, explain why only small amounts of helium are found in Earth's atmosphere. How would I do this? So I think this matters. I think the fact I know pressure is proportional to density, and I know that helium is extremely low density. So I might expect the partial pressure of helium to stay quite low. I know, let's see what else I know. I know that, let's consider the Earth's atmosphere like at the surface of the Earth. I know that the air at the surface of the Earth is all roughly the same temperature. And because it's the same temperature, I would expect it to be moving at the same speed, because that's what temperature is. It's a measure of the average speed of a particle, or the average kinetic energy of a particle, which is, kind of what this equation tells us. So I'd expect them to be moving at the same speed. I would expect the helium atoms to be very small compared to other particles. I would therefore expect them to have. Oh, wait. Oh, hang on a minute. Is this correct? I'm onto something here. So, the average kinetic energy of a particle is the 3/2 kT. If T is the same, the average kinetic energy of the particle is the same. But not all of the particles of gas in the atmosphere are made of the same thing. They have different masses. Helium has a very small mass, so I would expect it to have a higher speed than other particles on average. That feels like it might be relevant. And I'm probably not going to get to a fully correct answer here, but I'm showing you this process, right? Laying down what seems like it could be. So I think I've pinned this down. By the way, if this was wrong on the real thing, someone would intervene and stop me and correct me, nudge me on the right path, etc. But that's what I think, right? I think I could be onto something there and say that the helium would be faster moving, but it would be faster moving in all directions. The average speed should still be 0, so I don't expect why that means it goes flying off, apart from the fact that I do know it's lower density, and so I might expect it to float, but that doesn't make sense because it's not. How does the density come into play? Because if I had gases that weren't mixing. Oh, escape velocity. Clever. Oh, I like that. So good. At this point, they wouldn't have said it that explicitly. They might have said, oh, but for it not to be in the atmosphere, it must have left the Earth, shouldn't it? Or something tangential. And you go, oh, escape velocity. So then you can tie that into, well, let's talk about escape velocity. Escape velocity is when the kinetic energy is sufficient to overcome the gravitational potential energy. So we know this is the kinetic energy, that's the kinetic energy. And that has to be bigger than g m over r for the given particle. So 3 over 2 kt, where that's the mass of the Earth. So how would we establish the escape velocity of a helium atom from the surface of the Earth? Well, I mean, qualitatively, we've kind of done it, but can we do it quantitatively? I don't think they'd expect you to know these quantities off the top of your head, and they certainly wouldn't expect you to calculate it without a calculator. But so I think qualitatively that should suffice, that the speed is higher. But the kinetic energy, though, let's think about escape velocity in general. Escape velocity in general would be given by this. Cancel, cancel. 2gm over r square rooted. Okay, is v. And as we see here, c RMS squared is equal to 3kt over m. And when that is equal to 2gm over r, then you've reached escape velocity. So as the mass goes down, it's easier to reach escape velocity, which is true for the helium atoms, which are very light. That's really interesting. I'm really glad you brought that question, because also it gave me a chance to show something sight unseen that wasn't prepared to sort of see, because you just watched it in action, right? In a situation where I have no idea what to do, that's exactly, you've just seen what I do. And you can employ exactly those same skills. Throw something at the wall that demonstrates, because again, even if you don't get all the way there, look how many things I demonstrated I did know, right? And so I demonstrated if the question had been about those things, I would have been fine. So I show them everything I'm fine with, and it gives me some time and space to put it together so I don't feel like I have to get there instantly. And also the act of talking myself into it is what kind of gets me to the right answer. And then with a little bit of a nudge, like the nudge you gave me, then I was able to get there, right? This is interview technique. Also happy if anyone else has any other questions they've seen that are kind of similar to that. Happy to get into those. But in the meantime, I wanted to talk, I'm going to stop sharing screen for a little bit to demonstrate what it would be like in a more conversational, similar to that, but slightly more conversational. Do I want, I can always start sharing screen again if I want, if it feels good. Okay, so calculate the volume of the atmosphere. Those types of questions. No, okay, fine, we're here. That's let's get into that. So the more calculation based, there's one type of question which is so, it's like the question for physics, right? The one that they love, which is similar to this. How many ping pong balls could fill the room that you're currently in? So I'll talk, that one is a very physics based question, and it's only really asking that you have problem solving skills, and it's not asking you to get a precise number, it's asking you to be good at estimation. You're only really looking for it to be accurate to one significant figure. So for instance, the room that I'm in now, let's say that's like 4 meters that way, 2 meters that way. I can basically touch both walls. There's a bit of a bay window, so I'm going to ignore that. I'm going to ignore the closet there. What am I doing right now, by the way? Look at the assumptions I'm making. I'm going to ignore this. I'm going to do that. You have every right to state assumptions, commit to a process, get to the end, and then evaluate whether those assumptions were accurate and would have changed your answer. So I'm committing. I'm not asking, ooh, can I do that? Can I do that? I'm saying I'm going to do that. I am going to ignore the bay window. I'm going to ignore the closet. So I'm going to say it's 2. Everything's fine. So it's 2 by 4 by 2 is like 16-ish meters cubed. So why don't I lay that out? So the volume of the room is 16 meters cubed. Ping pong ball. Is that a ping pong ball? I'm going to say it's on the order of 1 centimeter radius, and I'm going to make for an assumption. I'm going to say that a ping pong ball fits into a cube of side length 1 centimeter. So the volume of the cube would be 1 times 10 to the minus 6 meters. So this is on the order of 10 meters cubed. So 10 over 1 times 10 to the minus 6, I'd be able to fit on the order of 10 to the 7 ping pong balls in here. Now, realistically, is that an overestimate or an underestimate? Realistically, I think the ping pong balls could fit slightly closer together than assuming they're straight cubes. Outright stating assumptions that they haven't been specified? Absolutely. Because they love it. Because it shows, like, stating assumptions shows that you have considered how to simplify the problem. And the most common mistake is to actually realize that you've made an assumption. Well, not even realize. A lot of the times people make claims not realizing they've made an assumption. So if you state outright, these are the assumptions I've made, then it shows, you're in on it. You know what you're doing. So yes, absolutely state every assumption that you ever make if you want to impress. And then you can evaluate it like I'm doing now. So I made the assumption that a ping pong ball fits in a cube. Realistically, I wouldn't expect that. I'd expect them to be able to fit a little bit closer than that. So that would have underestimated the number of ping pong balls. I also dropped that down from 16 meters cubed to 10 meters cubed, which would also be an underestimate. So all in all, I'd say that's an underestimate. It might be a little bit more. So it might be 2 times 10 to the 7, but it's still going to be on the order of 10 to the 7. Something like that. Or maybe I've underestimated the actual size of a ping pong ball, in which case I'd be able to fit fewer. These sorts of things. But the process is the point. Stating the assumptions and evaluating how they've affected your calculation is the point. So let me get back to Michael's original question, which was, how would you calculate the volume of the atmosphere? The volume of the atmosphere. Okay, so what am I going to do for that? Again, sight unseen question. Thank you for that. How would I approach that? Well, I know I've got an Earth, and I know I've got an atmosphere. That is the radius of the Earth. I don't know how high the atmosphere is. So at first, I could make a sort of... Okay, so it's going to be... If this is the height of the atmosphere, I'm going to call that. So then the volume of the entire atmospheric sphere would be 4/3 pi times 1,000 kilometers. I would have said 100 kilometers. Is it 1,000 kilometers high? Interesting. Are you sure it's not 100 kilometers? It's a 1,000. We have some dispute in the comments about exactly, but the point is the actual knowledge, the fact of 10 kilometers, 100 kilometers. All bets are off, guys. We have no idea how high the atmosphere is. But also, it doesn't matter how high the atmosphere is. Truly does it not matter. Because that is a fact. You can look it up online. You can look it up in a reference book. That's not the part that matters. Because that's not what they're testing. Planes fly at 30,000 feet. Yeah, which is about 10 kilometers. So there's definitely atmosphere there. Do you have any advice on how to do this to all different types of scenarios? Never going to be able to do all the scenarios. Like, what are you assuming? What estimations? This seems fun to do for lots of everyday things. Yes, can confirm it is. But the idea is, in fact, what you can do is you can try on these problems and just see what your brain is doing and clock it. Be very aware of every assumption your brain's making, right? So here, let me carry on with what I was doing here. It would be 4/3 pi times... In fact, why don't we... Okay, because I don't know the specifics, I can make a general expression into which I could insert the random numbers. And then we'll be fine. So that volume minus 4/3 pi r cubed. Do I have... Yeah, can confirm I have a student in the chat who's... Lol. So what I'm going to do now, pi, so that's going to become radius of the Earth cubed. Am I going to be bothered to do this? Yeah, let's go on. So 3r, in fact, I'm just going to call that r and h, just because I can't be bothered to write this all out. 3r squared h. Because again, look at what's happened. This has just been dragged back into syllabus material that I can demonstrate my understanding of. 3rh squared plus h cubed minus 4/3 pi r cubed. So it's going to be 4 pi r squared h plus 4 pi r h squared plus 4/3 pi h cubed. So that is the expression for the volume of the atmosphere, into which I can plug in the radius of the Earth and the height of the atmosphere. I'm wondering if I can make some sort of simplification. For instance, if h is very much less than r, I will be able to neglect this high-powered term of h. I know that r is approximately 6,400 kilometers, and I'm going to stick to the fact that the Earth's atmosphere is 100 kilometers high. 1/64, that does seem low. So if I were going to approximate it, if you wanted me to actually put some numbers to it, I'm not sure I would want to calculate all that. So how would I simplify it? I could say that feels significantly less. 1/64 is less than 0.1. I think I can make the assumption I'll ignore this term. And then what am I going to do? I could say, if I were to do that, then it would simply be this, into this, and this stuff. You got that, right? Good. So 4 pi times 6.4 times 10 to the 6 times 1 times, well, I'll call that 0.1 times 10 to the 6. So they're all in the same power. Times 6.5 times 10 to the 6. So I'd have 10 to the 18 right off the bat. And then 0.1. So 4 pi is going to be roughly 12. So roughly 1.2 times 6.4 times 6.5. Let's call that 6.5. Let's see if this goes nicely. 2/5, 32/5, 13/2, cancel for 16. Not nice. So let me estimate it. Can I be bothered to estimate it? Let's say this is approximately 3. 39, 40, 240/5. Mental math. So basically on the order of 5 times 10 to the 19 meters cubed would be the volume of the atmosphere. These are the sorts of things I would do. Now, again, does it matter that I didn't exactly get the mental math there? No, because they know they can use a calculator. Now, granted, sometimes they will be sticklers and will tell you to sort of do it properly, but that's somewhere they can go, right? Different interviewers are going to want slightly different things. So if you've got a pedant of an interviewer, they will let you know. Then you decide, okay, I'm going to take the time, develop this, make sure I get a right answer. So you just want to give them a sense of potential with an interview, because it could go absolutely anywhere. And so what am I thinking about that? So you want to give a sense of leave them wanting more, in a sense. Like, oh, this could have been, they want to give a sense of oh, this could have gone forever and ever and ever. There we go. 5.18 times 10 to the 19. So that's how you get close enough, right? By using your assumptions and making approximations. And so, for instance, that was 48. I decided to round up as well because I knew I made some underestimates along the way, right? And so it shows how close you can get and how good your assumptions can be, especially if they're asking you for these approximations and assumptions. They only want it to be good to one significant figure anyway, and it worked. I got it close to I got it correct to one significant figure using my assumptions. If I wanted it to be more precise, I'd have to refine the model and do some things that I couldn't do in an interview. But yeah, that's what they want. So now, Also, I really like this, by the way. This is good fun. If y'all want to keep on like peppering me with random questions and just watching me react, I am so down for that. But in the meantime, in the absence of other things, I'm gonna go on to this more conversational based one that I wanted to do. I'll try and find some. This is fun. All right, but if you're gonna try and find some, try it. Let's pivot onto this new style, right? Because I want to make sure you're good and ready on this. So this is one I've been doing with my students recently, and it depends. So there's one online you can look up. I think it's I can't remember. It's one of the Oxbridge colleges, and it's talking about getting in for engineering. They discussed it already. So to summarize this video, they ask what happens to a plane's jet engine in the rain. Does it get more efficient or less efficient? And so in the video, they talk about how you can approach this in a number of different ways. And again, that's so open-ended. It's not asking you to solve a problem. It's asking you to discuss an idea. So this is more about laying down the factors that could be relevant. So one factor that could be relevant, the density. Well, let's first discuss how jet engines work. Jet engines take air and then they fling them out the back, giving them speed. The air has been given momentum in a backwards direction. By conservation of momentum, total momentum before equals total momentum after. So the momentum of the air being thrown out the back of the engine is equal to the momentum gained by the plane. And so that's how jet engines work. If it is raining, that will increase the density of the air, which means that more momentum is sort of thrown backwards, as it were, which means that the equivalent by Newton's third law, it then gives, because resultant force is the rate of change of momentum, the engine gives a force to the air backwards, and by Newton's third law, any two objects interacting exert equal and opposite forces, which means force of plane on air equals force of air on plane, so you get a forward force on the plane. Okay, now if it is raining, density increases, the momentum increases, so the rate of change of momentum increases, so the force increases, and you might expect more force to come out of that if you're throwing back heavier air. So it might be working better that way. Or you might consider the temperature of an engine. So the engine is running a bit slower, which actually decreases the efficiency, if that's something you know. But then that got me thinking along different lines. And I will actually start the screen share again, because I think I want you guys to see what I've got in mind for this. So you've got your jet engine, and let's consider a single blade of the jet engine. And let's say it's got some water that has hit it. Let's ignore, the question's going to be, and let's say it's rotating in this direction clockwise. What's going to happen to the water? Again, these more open-ended questions. So you could take this in a number of directions. So you could say mass of the displaced air increases, but doesn't the velocity it's being thrown at decrease? So no overall increase in momentum. Interesting. I don't know that's correct, that the momentum goes down. Why is it given momentum? Because I'm not sure it's just the turbine blades that are giving it momentum. I think when you dig into the function of the engine, it's more to do with the air being brought into the chamber, the fuel being ignited, and it being raised to high temperature means it wants to occupy a much bigger volume. And so it kind of gets erupted out the back due to the increase in volume, due to the increase in temperature from the fuel igniting. So I think we would need to dig a little bit deeper. So you may be right, but let's think about what's happening right now, right? Assumes kinetic energy is constant. Kinetic energy is constant. Does it assume the kinetic? Well, it would assume the kinetic energy is constant if we assume it reaches the same constant temperature in the engine, because from the gas laws, temperature is a measure of the average kinetic energy. And so if the temperature of the engine stays constant, then the kinetic energy should stay constant, correct? Something like that. But the point is, if you're imagining I am the student in the interview chair, look at what I'm doing right now. It doesn't matter. I actually don't know this answer because I'm not a rocket scientist. But look at how I'm bandying with the ideas. And it's giving an interviewer the sense that, okay, if I sat down and someone did teach me the specific route for the specific question, I would be able to grapple with that idea. I would get to a point of being able to do that. And also, let's look at what I just did answering that question. So I laid out what I thought my initial thought was. Someone threw me a new idea. I considered that idea, really considered how it would have changed my answer, and then did something like that. So this process is all the sort of stuff you would want to demonstrate. Isn't more energy needed to evaporate water? So then there's like a little bit of loss of efficiency. Maybe, but let's think about, again, if we're thinking about assumptions that you've made, what you're assuming is that the liquid water makes it into the engine and that energy is used to evaporate that water, as opposed to why isn't it could be water vapor, which is already gas in the atmosphere, which doesn't require further evaporation. And that actually ties me back into this question that I was discussing, which is what happens. So let's say there is, obviously it's raining, there is physical liquid water in the air. But if you imagine that's hitting the turbine, is that making it into the engine? How much of it's making it into the engine? Because what you can imagine is from your day-to-day life, your real world understanding, you know that water is going to get flicked off the turbine blade. It's going to get flung to the outside. And so if I had sort of drainage here, the liquid water could be drained away and not make it into the engine. And this part is what I want to sort of zero in on, right? This idea that I said, from my common understanding, I understand that water on the turbine blade is going to be flung. Well, what do I mean by flung? How can we understand this flinging action? Oh, sorry about that. All the sake water's got me thirsty. So, let's consider this drop of water and what is trying to happen. First of all, let's sort of gain a little bit more real world understanding to get a high level qualitative sense of what's happening. Hits the blade and thrown off in an arc of circumference. We'll talk about it. So if I had, for instance, a sword, if I had a sword with some water on it, and I flicked the sword down, clearly I would expect the water to be flung down, sort of tangentially. So can I apply that understanding to here? So I might expect the water to be flung off in a tangential fashion. But then why is this happening? All right, let's think about this. So if the water was stationary, but the blade was moving, it would want to sort of move with the blade initially. So in order for it to accelerate up with the blade, there would need to be a force acting in the direction that the blade is moving. So as the blade starts to rotate to the left, I might expect there to be some force acting on it to get it to move with the blade, which would be caused by surface tension or friction. Well, we'll get there. Oh, we'll get there. So the question was, doesn't that assume the friction between the water and the blade is large enough? If the blade is smooth enough, the water would just kind of stay there. True. Well, let's assume there is some friction to start with. So let's make the assumption that there does exist some friction. And if there exists any friction, then there is a force and it would cause the water droplet to start to move. However, what we know is that the blade it is trying to move with is moving in a circle. And so the force required to maintain the droplet moving with the blade in a circle would be mv squared over r. And we can see as the water tries to accelerate to the same speed as the blade, as the speed increases, the required force to maintain circular motion also increases. But we know that friction, which is the force providing the centripetal force, which acts towards the middle, has a limiting value above which it cannot go. So eventually you hit your limiting friction, and if the required force exceeds that, then the force actually acting on the water is insufficient to maintain circular motion. So let's talk about what that means. Well, that means, because if you think, this equation only works for circular motion. Let's think about forces on non-circular motion. That is true. Max friction equals mu times the normal reaction force. The coefficient of friction times the normal reaction force. So exactly, you can take this point to demonstrate you understand that. And specifically, that would be static friction, because it would not be moving relative to the blade. But now, let's consider forces that are not equal to mv squared over r. So we know from Newton's first law that an object wants to stay at rest or keep moving with constant velocity unless acted on by a force. So when F equals 0, we get straight line. When there is a force, it causes an acceleration, which in this case would cause a deflection. This is when the force is less than mv squared over r, and when force is equal to mv squared over r, then the force deflects it sufficiently to keep it moving in a circle. So when the force that we have is less than the force required, we still get deflection, but not sufficient deflection to keep it moving in a circle. Relative to the blade, it gets flung to the outside. And so we might expect it to get flung like that, in sort of vortex action. What if you draw a side-on view of the blade, like at an angle almost, and then treat the whole thing like a banked curve? Ooh, interesting. Interesting. Okay. I have no idea what that's going to do, but that's almost the point. Let me put myself in your position in an interview and see what that would do. So correct me if I'm wrong, Farpoint, but I'm seeing, because I think what you're suggesting is that the blade itself is twisted, right? So it's not like a sort of it's not being it's not lying flat, it's sort of twisted, so it's on an angle. So if that was the case, and it was angled and moving sort of into that angle, I would expect a normal reaction force to be acting that way. Oh, but that's interesting now, because now it is not friction, because if I know from my syllabus, banked tracks are used to explain, I know that case study. That case study is for how cars move on a banked track without there being any friction. So if this thing was curved and was almost catching the rain, you can almost see a situation where the rain doesn't move. It just sticks to the blade and it almost gets like flung back with like the sort of G-force of it all, but doesn't experience side-to-side friction, which causes it to fly at all. In that case, it could keep moving in circular motion. Interesting. Well, let's discuss. So let's consider what would be required for frictionless carriage, if you will. So if that's theta, that's weight. So the component, there's a component of weight acting there. There's a component of the weight acting down. The center of the circle would be here. So this would be your resultant force. Okay, clearly weight has no component in that direction. That is theta. So that is theta. And so what you would get, if that's the reaction force, you would get the component of force acting towards the center of the circle would be r sine theta equals mv squared over r. But the reaction force, by resolving vertically, we get r cos theta is equal to mg. And so by dividing through, we get that tan theta equals v squared over gr. Now that's interesting because we actually know what v is. Can you specify how the blade moves in this viewpoint? Yes. So, okay, fair point. So I'm imagining the blade is sweeping through into the plane of the page and kind of going around. I'm imagining rather than sort of a blade being cutting through flat, the blade is like that and cutting through sort of at an angle. So this would be sweeping through past my eye into the plane of the paper, rotating about a point, which is somewhere over here, if that makes sense. So if this is rotating into the plane of the paper away from me, the center of the circle is over here, and the centripetal force would need to act towards the center of that circle. This would be the equation required to keep you moving without friction up and down the banked blade. And so this theta would be the sort of banking angle, the sort of tilting, curving angle. The reason why I find this interesting is because let's assume that the blade is rotating, but if you use friction, then sideways is... That's true. The reason why I've brought it to this place is because I remember this case study for frictionless travel. But if you use friction, then sideways is r sine theta plus mu r cos theta. Because r cos theta is mu r. Is that true? Would it be mu r cos theta? Because friction would be mu r, and r is mg over cos theta. Oh, no. Sorry. Yeah, I get what you're saying. So you're saying if we're assuming friction, it depends on which direction the friction is. If the friction is acting up the slope, or let's assume it's wanting to be flung to the outside, then friction would be acting down the slope. So that would be mu times... That would be mu r. So that's where the mu r cos theta coming from. So you're right that if... Okay, so what you're suggesting is let's introduce the idea of friction now. If we introduce the idea of friction, which way is the friction acting? I can tell that, let's say that the water is trying to be flung to the outside. The friction would be trying to resist that by having it act down the slope. That would therefore be mu r, which would be acting down the slope. The component of that friction acting towards the center of the circle would be mu r cos theta. So the new F equals ma acting towards the center of the circle would be r sine theta plus mu r cos theta, which would be equal to mv squared over r. Wait, so how is the blade connected to C? This is okay. So let's instead... You're right. I'm gonna have to draw this out so you can actually see this. How do I do this? Because I am not an artist. Okay, so blades. There are blades. Nope. Let's assume I kind of take the tip of the blade and twist it just a little bit. So let's assume, therefore, so it's twisted. How would I draw that? So let's take a side view of this blade. The blade, if it was laid flat, it would just look like that. But because it's twisted, it now looks something like this. If that makes sense. So if anything, we could then. But the point is, it moves in a horizontal circle, not a sort of sloped circle. So the circle it moves in is still flat, even if itself is curved. It's sort of leaning towards the angle it's moving in. This makes sense. Well, how else can I explain this? It's hard because I can see it in my head, which makes it unhelpful. So if you just imagine like sort of slicing air versus turning your hand in the direction it's moving, it's kind of doing that. So it might be worth moving off this because I'm not sure it's entirely. Oh no, you're right. Am I even considering the right angle? Let me put it this way. I think this is unhelpful for me to do now, where I think the feedback is less certain. So I'm going to move off this example, but still, I think Now, by the way, realistically, this might worry you and think, oh my god, what if they ask me a question like this where I can't understand physically what's happening? They wouldn't, right? They've sit there, they've planned it, they know exactly how to articulate the question, they know how to remove any ambiguities. So this is kind of like in the mechanics paper where you say like, oh, it's moving in a horizontal plane because they've accounted for like every possibility. Don't worry about that. This is only because I'm like making this up on the spot and sort of in reaction to what someone is saying. So we'll abandon that attempt for now. Just because I don't think it's like working very well. But I think the point, coming back to this original case though, look at how I made this argument, right? About when it's before it was banked. Let's think about how I managed my way through that. Look at the things I was referencing: circular motion, Newton's first law, friction. All of this is stuff from the syllabus that you can use to infer new understanding of an unseen situation. And that's what they're looking for. They're looking for, when I see something I've never seen before, what do? I reach for my toolkit. What do I reach for, and how well do I use those tools to sort of cut my way through the thicket? And by the way, well, actually, do you recommend getting as much of a deep understanding of every A-level concept as much as you possibly can? Yes. Although I will caution as to what deep means. Deep does not necessarily mean you have seen every possible question already. So what they don't want is knowledge, right? They don't want, oh, I've seen this before, this is how you do it based on my memorization. By deep, I would say fundamental. By deep, I would say do you understand it? Like, this is kind of, do you read the textbook and it makes sense, or do you get it? First principles approach, absolutely. Absolutely. Can you break this down in micro slow motion? You see a water droplet moving on a turbine blade. Can you stop time and think, what exactly is happening? What exactly are the forces on it? I see a friction. I see a surface tension. It's trying to move. It wasn't moving before. If it was at rest and it's now trying to move, that's an acceleration. What causes accelerations? Resultant forces. So there must be a resultant force. That really deep, low-level understanding. Because those are the universal laws of physics that can apply to any situation, right? They are laws. So whatever situation you see is obeying those laws. And if you have that understanding running so deep, referring back to those laws must get you a correct answer. And that also has the added benefit of letting you retreat to somewhere familiar and safe. So rather than think about there must be some really weird combination of things for this really unseen question. No. It's the same thing you've done every single time. And it actually makes the question feel less scary. And you can kind of retreat and go, okay, I don't like that, but I like Newton's first. And so by bringing the question back to your skill set, it makes it more likely to go right. What are the most common topics asked in engineering interview? Okay, so that would be more of your forces, motion, and energy stuff. I would expect there to be some electricity, perhaps. Bear in mind, there's no way I can predict exactly what's going to come up because they can go in any which direction they want to go. But for an engineering interview, forces, motion, and energy is a must. Maybe some moments, because I think rotational physics is something that's very difficult to understand, is not often taught in class, but is accessible with a little bit of a push. And therefore, it's kind of the perfect subject to take what you already know from the syllabus and teach you something new in an engineering way, because rotation in engineering is so some of that, if you can. If I was doing an engineering question, I might also do some gas stuff, because if I think about engines working, there's a lot of gas laws, heating gases and gases doing work by sort of pressure and volume stuff. So gas laws, certainly, materials, thermal physics, that kind of stuff. I could so basically go through your physics textbook or your math textbook and think, how could this be twisted into an engineering application? And then do that. Do you have any advice on how to improve this if you are weak with some areas? If by weak with some areas you mean first of all, any specific stuff from the textbook, get really good at it. So start with the textbook, the first principles approach. Okay. From the same commenter. So in which case, I would take a question from your textbook that you could easily do without thinking in under a minute, and purposely see if you can take 5 minutes explaining it. Because a lot of the time you're so comfortable with how something works that you stop looking at why it works. Exactly. Keep asking why all the way down. Ask why 5 times. It's a great piece of advice. Yeah. So for instance, and in fact, that's probably going to be my next stream. So it's the only one I haven't talked about yet, which is syllabus material. So taking it back to basics and really thinking about why. But let me take an example. Let's think about what's a good example? Well, in fact, I think I gave the example, right? When I was talking about the water on the turbine blade, I said, oh, well, it's going to move and then it's going to get flung off. Okay, but why? Oh, because it doesn't have enough force to sort of keep up. Okay, why? But then you saw what I did. I was like, well, it starts from 0. And instead of moving on from that, just sit there and look at it for a while. It starts at rest. And then it's trying to move. So how is it trying to move? Well, because something has to be pushing it. Because of Newton's first law. Something needs to push it to get it to move. Okay, well, what's getting it to move? Well, there must be a friction, and kind of do that. Basically, just ask yourself a whole bunch of questions. Be that little 4-year-old who goes, why? So ask yourself a question, then answer the question. Then ask a question, then answer the question. What if you fake that you haven't seen the question before? You can't. They'll see brains firing. You can't fake that. So you can tell the difference between, in my videos, you can tell the ones that I'm comfortable with because I've seen them before. And then you can see the moment where I'm genuinely like, oh, okay. Because like it by the way, it slows you down. Skip back through this, right? The ones where I've explained it before, I'm good to go. Look at the ones where you gave me something on the spot and look how slowly I have to talk to go, well, it's this, and that makes it this, and that makes it this, and that makes it this. And that slow churn is something they want to see, and that can't be faked. Are they likely to standardize the questions for interview, or is that up to the professors? So they will not standardize between colleges, but everyone within a college I would expect to get answered the same questions, and thus it will be standardized within a college. So you will be marked relative to your peers on a level basis. Um, I'm not quite sure how they calibrate it in terms of pooling. So, for instance, they might decide you're good enough to be accepted by someone, but they just happen to have a very good crop this year, so they will put you forward to the pool, which means that other colleges will be allowed to pick you up. I'm not sure how they calibrate it for what types of interview question were asked, but realistically, I think they get it, right? The supervisors get what the standard is for first year of Cambridge, and they're all going to sort of no one's going to calibrate it so that they have a really, really, really hard interview that puts off a load of people because you're just not going to get a good crop, right? Like it's in everyone's best interest to ask questions on a different level, and I wouldn't worry about that so much. Why should I do that, sir? I don't know when exactly that was asked, so I don't know what exactly that was referring to. Also, I have found out some other interesting questions. If you would want any of them, I would want some of them, but I do have to stop there. We've run over a little bit, so we're at 1 minute 10. I do have a session starting now, so I have to end the stream here so I can start my Zoom chat and do my one-on-one session. But I have rearranged my schedule, so this time, in fact, I might start a little bit earlier if people have more questions, so I can do from 6:30 on Thursdays moving forward, except for next week, I don't think. I'll have a think about next week. But I'm going to keep doing these live streams. If you keep having questions you want to throw at me, it'll give a good opportunity for me to demonstrate what it is to be student side on this. So Edward, if you want to join in, you can either leave it in the comments and I can look at it ahead of next time, or you can hold on to it, join a stream in future, pose it to me then, just to see what that does. But yeah, I think you'd appreciate that. Great. So I'm going to keep populating, especially these interview streams. I'm going to populate them ahead of time so you have plenty of notice of when I'm going to go live. So keep on top of that. Feel free to hold on to the question. I'm going to leave you there because I've got to run. But keep working hard, and I'll see you guys next time. That was fun. I like that. Let's keep doing this. All right. See you guys.